right, well, welcome back, and we're going to be talking about how to use cross-section to find the volume of a solid called, and this is usually called the slicing method. The slicing method. When I think of slicing, I think of slicing bread. And if you think about cross-sections, when you think about volumes of a solid, we find volumes by taking a cross-section. In this case, our cross-section is almost like a rectangle. All right, if you kind of think about that way, or maybe like some sort of other shape. Well, if you take this one slice and you find the volume of that one slice and you add up all the slices together, you can find out the volume of this piece of bread. Well, how do you find the volume of a solid? Well, really what you do is you take the area of the cross section. This is what this is. Area of cross section. And we're going to multiply it, all right, by its width, okay, or at height, or length or height, depending on what you have. And actually, that's how you find the volume of any prism. And what we're going to do is that we're going to take these small itty bitty cross sections. So if you had the slice of bread and you go really, really skinny, all right, and really, really thin, tiny little thin slices all the way through, and we keep on doing that, well, we'll have an infinite amount of slices, and this height, this width, all right, of each one of these slices is going to get infinitely small. And as you can see, this is turned into a Riemann sum, all right, where we're taking the area of the cross section times width, which actually gives us the volume of each one of these small cross sections. All right, that gives us volume. And then we're going to go and integrate this from A to B so we can add up every single one of these volumes together. And that's what we have. So my little steps are, in order to solve for volumes of cross sections, is we always going to sketch a picture if we can, find the formula for the cross section in terms of x, so the area, find the limits of integration from A to B, and then integrate A to x to find the volume of our solid. All right, so let's try to go through an example here. Here's our first example. And what we're doing is we're going to be taking a cross section using squares. So base of this is going to be squares. And what we have is our base area. We're going to have this little equation, which actually is a circle. I'm going to take this, make it a little bit smaller. All right, is a circle. So essentially what we're doing is we're creating this circle, which is actually a unit circle, with a radius of 1. Okay, right there. And we're placing squares at each, all right, an infinite amount of points from A to B, all right? And so this is like one of our slices that we would have here. Now, since we have this, our key thing that we have to know how to do is how to find, all right, the area of a square. Since we have areas of squares, we know that's going to be s squared. Well, we're trying to figure out the sides in terms of s. Now, this is where the algebra comes in. Because we have this right here is our equation, we need to figure out what is this value. Now, usually when I find the lengths between here, I need to figure out what the value from here to here is. Well, this, in order to figure the functions, we're perpendicular to the x-axis, right there, is that we need to know this equation. And so when we solve this, we actually have 1 minus x squared, and then we take the square root. And if you recall, in the solve for y, we bring a plus or minus. So this top end is going to be y equals the square root of 1 minus x squared. And on this bottom side right here, this is where the minus comes in. So we have y equals negative square root of 1 minus x squared. Okay, right there. And I'm sorry for all of this icky writing. All right, so we have 1 minus x squared, which is located there. So now the question is, since I have this equation, which is a semicircle on the bottom, and this equation, which is a semicircle on top, how do I figure out the distance from here to here in terms of x? Well, since each one of these values change, all right, our side length is going to be, well, the top one, we'll call that y1, all right, and y2, we'll take y1 minus y2. So the square root of 1 minus x squared, all right, top minus the bottom, which is negative square root of 1 minus x squared. When we have that, you might have already seen what this possibly could be. Negative is positive, so we have 2 square roots of 1 minus x squared for our side length in terms of x. So what is our equation? Well, going back, we know that to find the volume of a solid, we find the area of the cross section is in terms of x, and multiply that by dx, and then take it from a to b. So right here, what we're going to do is we're going to take and integrate from a. So where does this intersect? Well, it's going to intersect at -1 to this one right here, which is 1. So -1 to 1 of our area, which is s squared. So we're going to take this s in terms of x. So 2 times the square root of 1 minus x squared. And we're going to square it in dx. So this is our area formula. This is like our a of x, area of cross sections. This is our width, and together we get a volume. All right, the volume. And so we can solve this right here. This right here gives us our volume equation. And then we just go through and solve it. And so as we go through here, we would square that. So we get a 4. I'll just put that on the outside. Make that a little bit nicer. So we got 4. And we're going to integrate from -1 to 1. All right, because 2 squared is there. And then the square of the square root gives us 1 minus x squared dx. And we can integrate this for, we have x minus, all right, x to the third over 3. And we'll go from -1 to 1. Plug those values in here. We have 4, all right, times the quantity of 1 minus 1/3. All right, that's our first one. Then we plug in negative, so we'll have -1, and then the negative cubed is going to be negative, positive, negative is positive, so we'll have 1/3, which simplifies to, what do we have here? 4 times, we get our 2. Right there is going to be a negative, so we have minus 2/3. All right. And so what we have then right here, keep on simplifying, 4, and we'll have this right here, which is going to be 6 minus 3 was 4/3, which is going to give us 16/3. 16/3. Okay. Now I'm going to do something here because we're going to go through a couple more. Okay. So you can see how we did this right here and going through this little example. Well, let's say I continue on, and let's say I want to take the diagonals now are going to be squares. So these are right here diagonals of squares. So if you think about this and you wanted to figure this out, well, how do you find the area of a square given the diagonal? All right, given the diagonal. Well, as we know, we have the sides, okay, sides. And if it's a square, we know these are 1 to 1 to equal 2. And so right here, to find this and put it in terms of d, is that we have s squared. Well, I need to put this in terms of d. So what are the sides in terms of d? Well, we know that s times the square root of 2 equals d. So s is going to equal d, all right, divided by the square root of 2. Okay, and to find the area of a square is we have to take s squared. So in this case, we're going to take d over the square root of 2 squared. That would be equivalent to s squared in terms of d diagonal. And so we have d squared divided by 2. Okay, that's our area. Now, once again, same object going through here. That's our same value. Now, the one thing is that this s, or actually not this is s, our diagonal length using the same thing, our diagonal in terms of x, because that's what we need to do next, is find our area. So our diagonal length is going to equal the same thing we had here, 2 times the square root of 1 minus x squared, because it's the same type of drawing, same kind of platform where we're putting this on. But the one thing that changes is our equation. So instead of being s squared, we're actually going to have our area with the diagonal, all right, right there, is going to be 1/2. So I'm going to put that 1/2 out here. D squared. And so we're going to have 2 times the square root of 1 minus x squared, that quantity squared. All right. We're still going from -1 to 1. And then we have our dx. And so what's our answer going to be? Well, we know that the integral right here right here, is going to equal 16 thirds, 16 thirds. And so what we have right there is 1/2 times 16 thirds, which is going to equal 8 thirds. All right, 8 thirds for our answer for that one. See how this is going through here? Okay, yeah, see that? Okay, I hope you see that. Let's go one more. Okay, let's say our cross sections are not diagonal squares, but let's say they are equilateral triangles. Now, if you don't know the equation of how to find the area of an equilateral triangle, well, let's say we have our side right there. The area of the equilateral triangle is the square root of 3 divided by 4, and then we're going to have s squared. Well, same drawing, except different equation. Our s is going to equal what d was over here because it's that length, which is the same thing as our other one, all right, that we found right here, okay? And so to find this new one, we're going to have s equaling 2 times the square root of 1 minus x squared. Well, to find this area, we have a different area equation. So it's going to give us a different volume, all right? So this is what our volume is going to look like with all these small, getting larger equilateral triangles here. Still going from -1 to 1. Square root of 3 and 4 are our constant. And now we're taking s squared. S squared is 2 times the square root of 1 minus x squared. We square that dx. Well, looking at this and finding our answer, well, we know square root of 3 over 4 is a constant. We know that this right here is going to equal 16 thirds, because that's what we had in the previous one. That's what we found out. And so when we solve this, we know we're going to have the square root of 3 over 3. 4 goes in 16 4 times, so we have 4 thirds times the square root of 3. Okay, and I'm going to write that a little bit better. All right, 4 thirds. I guess it turns to be the same thing. All right, square root of 3, so that's a 4. There we go. Okay, and our square root of 3 there. Okay, and so in doing this, what did we just find out? Well, depending on the shape of your cross section, that gives you a different type of volume. And really the key is identifying what's the area equation you need, because the area equation will determine what, all right, you're plugging into your integral. Once you figure out the area equation, you need to figure out what is a side length in terms of x or y, depending on what you go. All right, and you solve. Okay, well, 1 through 3 different examples of how to find volumes of solid using cross sections. I'm going to go through another video in just a little bit, but I hope this helps you out and understand this a little bit better. Good luck and God bless in the rest of your problems.